Hello, everyone, and today we will be reading our presentation on quantum tunneling, and I say our presentation because I'm joined with none other than Semispecula.
Hello, hi people. Glad to be here.
Yes, it's nice to have you over in our presentation.
Thank you.
So yeah, let's get started. Hope you enjoy. Okay. How does it work? How it basically works is that a particle has a small yet possible chance of passing through a barrier if it has enough potential or kinetic energy, and if the barrier is spaced out enough. And when I mean spaced out, if it's not that dense enough, if it's thin enough, So yeah, time to go to the next slide.
So, how does it happen mathematically? Because in every single physical scenario we use mathematics, because mathematics is the most fundamental, and it's like our lens when we look through science.
Yeah.
So how does it happen mathematically? Well, every quantum mechanical object has an assigned wave function. Well, what's a wave function? Well, it's a lovely question. So a wave function is basically a probability density. So if I were to put this in simpler words, it would be the probability of finding something somewhere, basically. And it's a mathematical representation. So we cannot say a thing is a particle or a wave. That's very important. We assign it a wave function because it acts like it. It isn't the wave function who is the object, it simply acts like the wave function. So this is very important. Even very important scientists make this mistake. Wave function is not the particle, it's how the particle behaves. It's very important.
Okay.
So now we can go to the next slide.
Okay.
So how does it happen again mathematically? Well, we see a small figure on the right. We see that when the wave is high, we have a higher probability of finding the particle. So you see how sometimes it goes up and then goes down again, then goes up, right? So let's say, for example, look at n equals 4, okay? We see it goes first up and then goes down, then up again, then it goes down again. Well, what does that mean? If we take the modulus squared, so it's a complicated language, I understand, but it's basically a mathematical operation. So we take our wave function, then we do some maths on it, then we get the figure on the right. And on the right, basically all the things which were going down on the left is basically now going in the up. You can think it that way. And that is the probability of finding the particle. So if the wave is high, you have a higher probability of finding it in that specific spot. And if it's down, there is a less probability of finding the spot. So for example, look at n equals 1, the first state, way on the bottom. We see that it starts from 0, then goes high in the middle, right? And then it goes down again.
Yeah.
So finding the particle in the middle of the box is the highest, because the highest of that curve is in the middle. So that's how a wave function works, basically.
Okay.
Now we can go to the next slide.
Okay.
So, this is a scenario where we apply the wave function. Do you see that small symbol which looks like an eye with some arms next to it? That's the wave function. It's the Greek letter psi, and that signifies the wave function. So as we can see, again, we can see the wave function. When it goes high, there is a higher probability of finding the particle. When it goes down, there is a less probability of finding the particle. And when we have a barrier, we can see in the blue thing, the wave function penetrates the barrier, and then it goes to the right. And this might look very mysterious to us because we're not used to this phenomena. However, mathematically, the wave function can do this just all right because it's how it's defined. It can penetrate barriers even if the height of the barrier is unreachable to the wave function, because it's a quantum mechanical phenomena, basically. And this happens because this wave function has solutions even if there is a barrier. And that's how it happens mathematically.
Okay.
Now we can go to the next slide. And who discovered quantum tunneling? Well, it was first discovered by, I'm going to be butchering his name, Friedrich.
Yeah, I think it's Friedrich.
Yeah, in in 1927 while he was calculating the ground state of the double well potential. And yeah, that's basically all from me.
Okay. Good job.
Thank you.
No problem. How common is it? Well, there is about a 0.1% chance that an electron will tunnel through a barrier, but in reality, this means that thousands or even trillions of electrons pass through a barrier, since there are probably more electrons on Earth than stars in our universe. Is that a good assumption? Or?
I'd say so, yes.
Okay. And it also takes on average about 0.61 milliseconds or 610 microseconds for a particle to pass through a barrier, which was determined by making rubidium atoms tunnel through a laser. So yeah, pretty nice. Fun facts about quantum tunneling. Fact number 1. Did you know that photosynthesis is affected by quantum tunneling by losing some sunlight due to photons tunneling by? Interesting. Fact number 2. Did you know that some scientists think evolution could be caused by quantum tunneling? So yeah.
Honestly, I've been studying quantum mechanics for a long time, and I didn't know these two facts. This is the first time of me hearing them, and they both make so much sense, honestly. And I'm very shocked and surprised.
Really?
Yeah, so good job by finding these.
Thanks. Then a little fun experiment with quantum tunneling. So first, what you need is a glass of water and your fingers. So, look directly down the center of the bomb without looking at the sides. Notice how you can't see the outside of the cup. Then, put your fingers on the cup and press your fingers on the glass. If you press your fingers hard enough, you can start to see them, the science behind it. So when you look down, there is a layer of air, that rhymed, that blocks the light from the sides. But when you press down on the glass, you are making this layer thinner and thinner to the point that is thin enough for photons from your fingers to tunnel through the glass. It's pretty cool. And then have some sources, This will be in the link in the description. And the end. Well.
The end. Brilliant. Good job.
Thank you. You did a good job too.
Thank you. It was a pleasure being here with you.
No problem. So yeah, his wonderful channel will be in the description as well.
I'm flattered. Thank you.
No problem. So yeah, we really hope you guys enjoyed and that you learned something new. And again, his channel will be in the link in the description. So yeah, I hope you guys enjoyed, and we'll see you in our next videos. Bye!